So integer programming is, as we talked about different types of problems, classes of problems, is a class of optimization problems where the variables are integer. But why do we need integer variables in our formulations? Because in reality, a lot of things, number of products to produce, whether a location should be chosen 0 or 1, sequence of 5 jobs in a process, these are all integer values that our variables can take. And because of that, we have to introduce integer variables to our problems. And when we have that, as you will see shortly, other methods or algorithms that we use for solving linear programming problems will not work. We have to have a new type of algorithms to solve them. And other cases where we have to introduce integer variables or 0 or 1 is, for example, either or constraints that we will talk about later, which is, for example, when we want to express in our constraints, either don't produce product A or produce, if you do produce it, produce more than 1,000 units. Either don't fly aircraft, or if you fly it, do it when all maintenance tasks are done. If then constraints, if the maintenance level is low, ground the aircraft and do maintenance. If aircraft is grounded, all maintenance tasks must be executed regardless of their due dates. And if you purchase an asset, fixed procurement costs will apply, will incur. If a hospital is built, then you have to also hire nurses. So in all these practical applications where we need to formulate the constraints, we will end up introducing integer variables, and for those we will have problems. Another thing is piecewise linear functions. So one of the conditions for linear programming was to have linear expressions of our functions would be linear terms of the decision variables. What if you're let's say for one variable x1, you have a function that looks like that. It's not linear. It's, for example, a square root of x1 or so forth. For cases like that, you can break that function to pieces, that those pieces are linear, and then with some techniques you can introduce 0, 1 variables that tell you which part of this which part is your objective function. Is it 1, 2, 3, 4, 5, 6? For cases like that, we will also end up introducing 0, 1 binary or integer variables. Let's say we have two problems, both with 2 variables. The first problem, maximization, 3x1 plus 2x2, x1 plus x2 less than or equal to 6. As you see, in this case, this is not an LP. This is not linear programming problem because it states that our variables are integer. And the second one also says that our variables are 0 or 1, binary. That's also not linear programming. So LP relaxation means that drop that constraint, ignore that constraint. So I'm going to turn this first problem. Everything looks the same. I just dropped that part that says x1 and x2 are integer. In the second one, when I write the LP relaxation version of that IP, so this is IP, integer programming model. This is LP relaxation model to the right. But if I just change that, what is it that's really changing? So if you have a integer programming problem, if you have an LP problem similar to what we had before, this is your feasible region. You have x2, x1, and you have this constraint x1 plus x2 less than or equal to 6. and your feasible region is to the left. So that's your feasible region, that entire triangle. When you say my variables are integer, your feasible region actually becomes a bunch of points. These points are 0, 0, 0, 1, 1, 1, 1, 0. So all of these, this is, for example, 6, 0, this is 0, 6, and so forth. This is 0, 0. When you have an integer programming problem, you're not working in a region, in a confined area. We're working with a bunch of points. And algorithms that we had before will be ineffective, such as simplex. So there are two things to talk about when we're talking about integer programming. One is algorithms that can help us find the optimal solution. And then we have some techniques in modeling. This week, I'm going to talk about algorithms that are used to solve integer programming problems. We have exact or generic algorithm methods. So simplex was a generic method or graphical method. Those are generic for LP problems. And we have a few: branch and bound, cutting planes, implicit enumeration, and so forth. These will solve any integer programming problem, regardless of what that problem is. So they don't pay attention to the structure. When a method is specifically designed for a special problem, that's called a heuristic. And if it's also generic and uses randomized solutions such as genetic algorithm or taboo search, those are meta-heuristics. We have already looked at some heuristic methods. We have seen one heuristic method for integer programming. Do you know which one it is? We saw some algorithms so far, right? What algorithms did we look at so far? Have we looked at? We had simplex. Simplex was for LP. Then last week and this week, we looked at a few algorithms, right? For transportation problem, northwest, but those were not integer programming. How about Hungarian method? Hungarian method, the variables were 0, 1. So it was essentially an integer programming problem. So Hungarian was a heuristic specifically designed for assignment problems. Hungarian for assignment. And then branch and bound is a method, generic method that, as I said, works for any type of problem. We're going to learn that method today. Branch and bound. So branch and bound, the general procedure is that first you solve the LP relaxation version of your problem. When you do that, it's going to have some solution. For example, x1 equals 3, x2 equals 5. If it's integral, such as the problem I told you, x1 equals 3, x2 equals 4. In this case, the optimal solution, you know what happened? In this case, the optimal solution is, in fact, all integer. So we don't need to do anything. We solve it. We solve the LP relaxation. The answer happened to be integer. So that corner point in the feasible region, for example, here happened to be 3 and 4. So we don't need to do anything, but that's very rare. Usually what happens is that one of these is, for example, 4.3. It's not integer. So if that's the case, we need to use the branch and bound method, which is we cut the feasible region into 2 pieces. That excludes that point. And then we solve these 2 regions. And then We branch on each. We do that until we find a solution that's all integer. And in doing so, we'll find an upper bound and lower bound. We'll talk about those. Another concept is that fathom. When you're branching, if for whatever reason you decide that you're not gonna continue exploring that branch, you say we fathom it, which means we stop here. There is no reason to explore it further. You will see why. There are a lot of very interesting, important concepts in optimization that we will learn in this explanation of branch and bound. Okay, any questions so far? Let's look at a problem. Let's say X1 is number of tables manufactured, X2 is number of chairs manufactured. And you have resources in terms of labor constraint and wood constraint. You know that each table and each chair take 1 unit of labor each. So 1x1 plus 1x2 less than or equal to 6. And then each chair takes 9 units of wood. Each table, each chair takes 5 units of wood, and you have 45 units available. And then you make $8 or 8 units of money per table sold and 5 per chair sold. So this is a classical optimization problem. So question here is, what is the optimal answer? What's the optimal solution? You may say, well, we have 2 variables. I can use the graphical method. I have 2 constraints. That's 1 constraint. And then probably that's another constraint. That's my feasible region. Just use either the graphical method or simplex to find the answer. The answer is going to be one of these corners. However, note that these variables have to be integer because you cannot produce 1.3 chairs or 7.2 tables. They have to be integers, the answers. As you see, this is how the feasible region looks. Your feasible region, in fact, is only these points, not the shaded area. Because the what is it? The variables are all integer, you only look at these points. And this optimal point for the relaxation, LP relaxation, happens to be happens that it's not integer. 3.75, 2.25. So it's not useful. It's not useful. So how does branch and bound work? So branch and bound, the way it works is, first you pick either x1 or x2, one of these variables that does not have an integer solution in the optimal. So step 1, basically, I solved the LP relaxation, which is this whole region, and I found this point to be optimal. That point is not integral. So what do I do next? I pick one of these 2 variables, x1 and x2. I'm going to use pick x1. And then we would say we branch on x1, which means 3.75, which is the value, optimal value for x1, is between which 2 integers, 4 and 3, right? So I create 2 sub-problems. This was the original problem. This was the original problem. I'm going to create 2 sub-problems. One problem says the original plus this new constraint, x1 less than or equal to 3. Another sub-problem. So this is sub-problem 1. This is the second sub-problem. x1 greater than or equal to 4. These are 2 new problems. So whatever was the original problem plus the new constraint, or a new cut, we could call it. Therefore, why do we do that? Because We want to make sure that we don't see this answer anymore. This answer, x1 equals 3.7, is neither part of this problem nor this problem. It will not appear in any of those. We will not get that answer anymore. So as you see, I have two subproblems. Subproblem 2 here, subproblem 1 here. Subproblem 2 is essentially subproblem 1 plus this constraint, x1 greater than or equal to 3. Subproblem 3 is the original problem plus, which means whatever you had there, plus this new constraint, x1 less than or equal to 3. Subproblem 1 is going to be this region. Subproblem 2, or this, basically I have two optimization problems to solve. And I solve each. If you solve each, so this was the original answer that we found. This was the LP relaxation. Now subproblem 2 and 3. When I look at the answer for subproblem 2, which is this region on the left, the optimal solution is x1 equals 4. Actually, I'm looking at this one, this triangle. For that one, x1 equals 4, x2 equals 9/5. Essentially, it's this point. Unfortunately, that point is not integer because x2 is not integer, right? So one thing happened though. When I solved the LP relaxation, the z was that, right? And when I solve a new problem, which is the original problem, plus a new constraint, what happens to the optimal solution? Does it get better or worse? How can you explain it? I'm adding a new constraint. It may get worse, but it definitely doesn't get better. Do you agree? So that 165/4 that I originally found is basically my, and this is a maximization problem. I'm trying to maximize the problem. That's called an upper bound. Do you agree? All right. So now I found this answer. It's 41. Now I need to do the same thing here. So this is my original problem now. Subproblem 2, this triangle. And I found the answer here, 4 and 9/5. And I need to branch on it. What do? I create two new subproblems. And I'm trying to get rid of that point, 9/5. 9/5 is between which two integers? One and two. So one is gonna say x2 greater than or equal to 2, x1, x2 less than or equal to 1. That way, I'm ensuring that I will not see that point anymore, right? So what happens here? I created two new subproblems, subproblem 4 and 5. Subproblem 4 is saying that x2, basically this was my original problem. Look at it. This is what I had originally had. Subproblem 2, the original, plus this constraint that says x2 should be greater than 2. What is the feasible region now? It's empty. There is no intersection between this and that original one, right? So this subproblem 5, sorry, this subproblem 4, which is the original triangle. This is triangle, subproblem 2. Plus this constraint, x2 greater than or equal to 2, is infeasible. That's why we do not continue here. We don't even check it. There's nothing to check. How about this one? It says the original plus x2 less than or equal to 1. This is your new subproblem. Subproblem 5. So subproblem 5 is subproblem 2 plus 2 new constraint, which is x2 less than or equal to 1. And subproblem 2 itself was the original problem, plus x1 greater than or equal to 4, which led to that triangle. Let's look at subproblem 5. If I solve 5, this is what I find. x2 equals 1, which is integer, but x1 now is not integer, right? Now I need to branch on x1. 41, 40 over 90, which is what? 3 point something, right? It's between 3 and 4. So which one is it? It's x1. So one constraint, x1 greater than or equal to 5, x1 less than or equal to 4. So problem 6 and 5. So this original problem that we had, it was this part, right? This was subproblem 5, the shaded area. This was 5. That plus this new constraint that says x1 greater than or equal to 5, which is this point. What is the intersection? It's just that point. Right? What is the intersection of that and x1 less than or equal to 4? It's this line. Do you agree? So if I solve those, 6 and 7. This is what happens. 6 gives me a nice integer solution. x1 equals 5, x2 equals 2. Objective function value, 40. We call this 40 because, so we already found one integer solution. This one also happens to be integer. Objective function 37. Which one is optimal? Which one is better so far? Because it's maximization, subproblem 6. This one is better, right? So out of these two, I'm gonna pick 40. I'm not gonna explore this anymore. And so far I have found an integer solution and its objective function value is 40. I call that 40 a lower bound. What does it mean? It means anything less than that, I'm not gonna explore. This is a maximization problem. I've already found the integer solution and it's 40. Anything below that, I'm not gonna even look at because this is already good. Like 37, you would say, don't even, just drop it because you already have a better one. So everything we did so far was exploring this branch of subproblem 2. Do you remember we started with the triangle on the right? We never looked at the one on the left, which was the larger portion, right? When we solve the LP relaxation of the left part, this is what we get. 3, 3, integer, and this is 39. But our lower bound is 40. So we drop that one too. Right? Because this one is already better. So this is the total optimal objective function. Why? Because there is nothing else to explore. We have explored everywhere. Does it make sense?
Can we just wait on Z at the beginning? It's 41 and it's crossed to the answer.
Z in the beginning. Where? What do you mean?
Z is 41, we know that.
Oh, here,
So
41.
yeah, so we can cross the other one.
Let's say we had started with the left part. Is that what you're saying? So remember, we had started with this triangle here. We started branching on that. If we had started branching on that part, we would get 39 and it would be integer. LP relaxation of the triangle part, subproblem 2, which is not integer, is 41. But so this would be my lower bound, 39. Right? Which means anything less than 39, I'm not gonna explore. Would you still branch on subproblem 2? Yes, because it's 41, it's greater than 39. It's a maximization problem. I know that when I branch on it, it's gonna get worse, as it did here. Went from 41 to 365 or 9, which is above 40. But I don't know how much it's gonna go down, but it has potential for exploration. But if Z1, for example, was 38 here, this is 39. This is 38 and it's not integer. Would you branch on it? No. Why? Because when I branch on it, it gets worse. When I add constraints to it, it gets worse. So why should I do that? I would say we fathom it. We don't explore it. So to summarize, this was our original problem. Choose a variable that has taken a fractional value in the LP relaxation or upper bound solution. We picked x1, which was 3.4. Create two subproblems. Subproblem 2, original problem plus x1 greater than 4, greater than or equal to 4, less than or equal to 3. Two new problems. Solve the subproblems, the LP relaxation versions. If it's integer stop, mark it as a lower bound. And then branch further if possible. Stop branching from a subproblem if it's either infeasible or it's already worse than the lower bound that you found. If it's a minimization problem, change all of these. Lower bounds become upper bounds. When your optimal solution is the current lower bound, when there is nothing else to branch on, when you have explored all the options. Okay. So this was the objective function. We branched on it. We branched on x1. That's why you see that it's cut into two pieces on the x-axis, x1 axis, because we branched on x1. And then we branched on x2. That you see that those two lines are on the x2 axis. Then from those, I got those two subproblems, and we found those and done. Any question about this? This is how branch and bound works, which is a very beautiful algorithm. Works for integer. But one thing I didn't explain is when we branched, when we got a new problem, I said solve the LP relaxation. How did I solve it? LP relaxations are LP problems. So I either use the graphical method or I use simplex. So at every new node that you get, you're running simplex to find the optimal solution for that point, for that problem, right?